Alright, this is part 2 of the lymphatic and immunity study guide. We're going to focus on immune adapted defenses. Alright, so adaptive defenses. This is related to a specific immunity to a specific pathogens. Your body is creating memory from different immune responses to later on target that pathogen within your body with a lot ease. It is going to be easier for your body to attack pathogens that have been present before, and that is because we will have antibodies in the body present to target those pathogens much easier. So to start with, before we dive into the entire process, let's go over the creation of some of these lymphocytes. So the creation of lymphocytes in the bone marrow, we determine that that is lymphopoiesis. Lymphopoiesis happens in the bone marrow. Lymphocytes originate in the bone marrow as hemopoietic stem cells. Hemopoietic stem cells. So these hemopoietic stem cells are cells that have a pluripotent capability. And what that is that they can divide into any cell that they are intended to. They could go into the myeloid lineage and become a red blood cell. They could go into the lymphoid lineage and become a B cell, a T cell. So again, lymphopoiesis, the creation of those lymphocytes, it starts in the bone marrow, and it starts with the hemopoietic stem cells. These cells divide and they produce lymphoid stem cells. All right. So this is another diagram that shows the breakdown. So we have the hemopoietic stem cell divided into two major categories: the myeloid lineage and the lymphoid lineage. Now we have other types of cells within that, and that is red blood cells, platelets, neutrophils, eosinophils, basophils, and monocytes that later become macrophages. All right. Now within the lymphoid lineage, there are three cells: B cells, NK cells, and T cells. You can better remember these based on where they are maturing. So B cells and NK cells are said to be bone marrow dependent because they are produced and mature in the bone marrow. T cells, unlike B cells and NK cells, they not only are created in the bone marrow, but they are then released in circulation and they go to the thymus. So we can say that the T cells are thymus dependent. T for thymus. All right. And in the thymus, they get trained in order to become immunocompetent. And what that is that we can make them ready so that they don't react to self tissues. We don't want your own immune cells attacking your own body. So in order to do this, these T cells undergo some training, and about 98% of the T cells that are produced are destroyed in the thymus, and only 2% are left over. And these 2% are the ones that are left to fight the immune response. In this chart right here, we can see with much more detail some of the different stages that the cells go through. So to begin with, we have the big picture here is we're trying to create a lymphocyte, a cell that is within the lymphoid lineage. And we do this by stimulating this hemopoietic stem cell. The hemopoietic stem cell is stimulated, and it will be stimulated by a specific hormone. If you want it to go into the lymphoid lineage, you will stimulate it with interleukin 7. If you want it to go into the myeloid lineage, you will use more so multi-CSF hormone. At this point, we're going to focus on the lymphoid lineage. So within the lymphoid lineage, once we have the commitment of the hemopoietic stem cell into that lymphoid stem cell lineage, then we can divide into three options, and that is the B cell, the T cell, or the NK cell route. Once we have committed, there are different immature lymphocytes stages, but nonetheless, they end up to a main product that is either a B cell, a T cell, or an NK cell. You are not supposed to know, you don't have to remember these names. Just know that if we're coming from a stem cell and there is a maturity process that happens, The T cells don't mature in the bone marrow, they mature in the thymus. B cells and NK cells do mature in the bone marrow. Okay? Key takeaways from this slide is going to be that we're coming in from a hematopoietic stem cell and we are committed to the lymphoid lineage with the help of interleukin 7. Again, so which type of lymphocytes are made and mature in the bone marrow? And we have two cells, and those are going to be NK cells and B cells. Blank is the hormone that stimulates this process. Remember that we have a hormone that helps the hematopoietic stem cell to commit to that lymphoid lineage, and that is going to be interleukin 7. Next, where do T cells go to mature? Remember that T cells are produced in the bone marrow and then they go to the thymus to mature. And there it is where they become immunocompetent so that they don't react with your self tissues. You do not want the T cells attacking your own tissues, otherwise you will have an autoimmune response. So where do cells go to mature? And that is the thymus. Blank is the hormone that stimulates this process. When we talk about cells that go to the maturation process, we're talking about thymic hormones. And these thymic hormones are the ones that stimulate the maturation process of the T cells. There are different thymic hormones, including thymosin, as well as different cytokines. Lymphocytes retain their ability to divide in the peripheral tissue. So T cells and B cells are located throughout the periphery, especially in lymphoid tissue. Remember that you have different types of lymphoid tissues. We have encapsulated, and that is organs, such as lymph nodes. We'll put in here lymph nodes, such as the spleen, such as the bone marrow, and the thymus. And we have without a capsule, and those are diffuse types of tissues, and that is related to malt. All right. Now, these other types of tissues or cells, such as B cells and T cells, can be in the periphery, and they can divide. They can divide because once they become activated, you need to create a large population of that activated cell to create an immune response. B cells differentiate with exposure of a hormone called interleukin. All right, and T cells differentiate with exposure of thymic hormones as well as interleukin. Once we want to expand and create more cells, we're using hormonal or paracrine signals, hormones that are released by nearby cells, so that we can make the T cells and B cells divide. I'm going to mention the process of T cell and B cell activation a couple of times. This is going to be the first time. All right. So remember that in our body we have pathogens. These pathogens have in their membrane antigens. Okay, they either be a glycoprotein or just a type of a mechanism in which it can be recognized. There are a couple ways in which it can be activating your immune system. One is by antigen presenting cells engulfing, such as macrophages. We have antigen presenting cells, different types, including macrophages. We have dendritic cells. We also have Langerhans cells, and we have also B cells. So these antigen presenting cells are trying to show the T cell what the pathogen looks like. In this case, we're going to use the macrophage example. So the macrophage is going to engulf this pathogen and is going to capture this process outside of the bacterium, and it's going to present it outside of a receptor. It's going to bring it over here and it's going to show it in this receptor. This receptor, we're going to call it MHC2. Okay, major histocompatibility complex. And this receptor, now that is shown here, It is meant to show T cells that may be nearby. We're going to put this as a T cell. So this T cell is going to come to this receptor and it will then become activated. The T cell will then understand that there is a type of pathogen with this type of characteristics, and it will go on to activate a B cell. The B cell now will know that this type of pathogen looks like this, and it will start to divide with the help of interleukin. This T cell is releasing interleukins, interleukin, so that the B cell, now that is activated, it divides. And the many types of B cells, once they are divided, then they mature and they become a plasma cell. And it is this plasma cell that now is going to create a antibody. And this antibody will be a molecule that will have a high affinity for this type of antigen. So when the antigen comes back later on, then this type of antibody, which will now be free flowing in circulation, we're gonna just devise circulation. We have multiple of these antibodies circulating. When this pathogen comes in, these antibodies will fixate to this area, and they will agglutinate, and they will create an immune response, activating maybe the complement system. Remember how we talk about the complement system activating itself to fixate proteins, for one, to cause inflammation, two, to enhance phagocytation. Once these antibodies are bound here, it is easier for those complement proteins to bind in, and then for the macrophage to come in and engulf and phagocytize this agent. This is one of the examples in which we're using adaptive immunity to create antibodies to attack in a future occasion those events. There is a cascade of reactions that are happening amongst these. This is a very simplistic view of what the immune response is, of how the immune response is happening, but that is the gist. We're basically attacking, learning, and then creating some memory outside of this process. Blank cells produce and secrete antibodies. Remember that B cells are the ones that will become activated. Once they become activated, they will divide. And once they divide into multiple numbers, then they will commit into becoming a plasma cell. And those plasma cells are the ones that will be involved in the antibody production. So to answer the question, blank cells produce antibodies. We're going to say plasma cells, which is a committed B cell to that type of antibody. There is a couple of ways in which B cells can be activated, and that is through T helper activation. B cells do not directly attack the invaders. Remember that the antibodies are the ones that are now free flowing in circulation for the future, so that the antibody can then bind onto the antigen that they are prepared for. There are some of these B cells that are dividing here that will become memory cells. So not all of them will become plasma cells. A lot of them do become plasma cells, but some of them will be going to memory. So in the future, when these memory B cells are activated, they will divide again to create a rapid development of that antibody. This process of activation of T helper cells into B cells takes time. So having that memory B cell already will save you a lot of time into mounting that antibody response. What type of lymphocyte is responsible for humoral immunity? Remember that humoral immunity is referring to antibody production. So if we're talking about antibody production, we're talking about B cells and plasma cells. B cells are responsible for antibody-mediated immunity or humoral immunity. All right. Here we're gonna discuss the second, for a second time, the way this antigen presentation is affecting or helping with antibody production. So remember that we have multiple ways in which we are protecting the body, and that is through mucosal associated lymphoid tissues. These mucosal associated lymphoid tissues are rich in B cells, NK cells, and T cells. All right, these are already mature T cells. Now, these type of cells are ready to recognize and mount an immune response. These mount are type of mucosal tissues that may be present in your tonsils, that it may be present in your gut, it may be present in your bronchus, and they have a rich amount of these cells to mount that immune response. So when a bacteria comes in, we're going to add to this amount, we're going to add antigen presenting cells. So, and within those antigen presenting cells, we have dendritic cells, we have macrophages, we have Langerhans cells, that those cells are actually specialized, Langerhans cells, and we have B cells. So the last example, we use a macrophage as an example. This time, we're going to use a B cell as an example. So B cells, once they become activated, they will secrete different antibodies, and some of them will some of them will go on to become plasma cells, and those will secrete antibodies. The B cells that were activated, some of them will commit to memory cells. So those memory B cells will stay around in circulation, all right, or the mold. If there is an antibody that, if there is an antigen that it recognizes this cell will then go on to show to the T cell. And let me draw the T helper cell. It will show that this antibody is now in circulation. If the B cell encounters a pathogen with a known antigen that it knew before, that the B cell knew how to attack, it is going to go on to show that antigen through an MHC2 receptor, so that these two match to activate the helper T cell. The B cell is, when it becomes activated, it will not only activate other T helper cells, but it will start dividing itself. So it will divide into different B cells, and some of them will go on to plasma cells, and then those will produce antibodies. Some of them will also retain the memory. And now we have a double effect, because the helper T cell, it is now going on to activate multiple other cells, such as macrophages. It will go on to activate other B cells again. So other cells, other B cells that had not been recruited, it will be recruited by the helper T cell. So when this pathogen is engulfed, the helper by the macrophage, the helper T cell, we're gonna say that this is macrophage. This helper T cell will tell the macrophage to go ahead and destroy this pathogen. There are multiple ways in which we can create antibodies, but as you can see, we have a couple of players into this process. We have B cells, NK cells, T cells, and antigen presenting cells. The antigen presenting cells, their main role is to gather up information about the pathogen so that they can present it to the T cells, more so the helper T cells. Once they have activated the helper T cells co-stimulate themselves, as well as the other cells to mount an immune response. The overall purpose of this is that we want to tell the B cells that there is a pathogen that looks a certain way so that it can then create antibodies specific to this type of antigen, to this type of pathogen with certain antigens. Next, we have antigen presentation. What does it? Who do antigen presenting cells present to, and which MHC proteins do they use? I just wanted to recap. So we have different types of lymphoid cells. So let's go ahead and write them out. Lymphocytes. Let's just write lymphocytes. So we have B cells, we have T cells, and we have NK cells. NK cells, B cells, as we mentioned, once they become activated, they will divide and then they will mature into a plasma cell. And it is that plasma cell that will then produce antibodies that are specific to a pathogen. T cells have different types. So we have a T helper cell. We have a T cytotoxic cell, and we have T memory cells. We have T regulatory cells. So remember, we have about 4 types of T cells amongst many others. But overall, these are some of the major players. The helper T cell is the one that, as we saw before, is the one that is presented the antigen so that it can then activate B cells. Okay, so antigen presentation from antigen presenting cells. Remember that we have different types of antigen presenting cells. Those are dendritic cells, Langerhans, macrophages, and B cells. And these antigen presenting cells will be presenting to the helper T cell what the pathogen looks like so that they can mount an immune response. Now these helper T cells will be presented, what the pathogen looks like through an MHC2 receptor. So these antigen presenting cells, either be dendritic cells, Langerhans, macrophages, or B cells, will show helper T cells what the pathogen looks like through an MHC2 receptor. I'm going to put it here. There is another type of T cell that is a cytotoxic T cell. This cytotoxic T cell, it is more involved into the destruction of pathogens. So cytotoxic T cells are monitoring for MHC1. Cytotoxic T cells are checking this receptor on cells. And I want you to think of the MHC1 as a receptor that is displayed by your own tissues, muscles, different types of tissues within your body have a specific receptor that is called MHC1. So let's make it purple. And it looks a certain way. And it is kind of a health status ID card that the cytotoxic cell is checking. Because when this cell becomes infected by a virus, or there is some type of cancer, there will be changes to this ID card. And once it changes, the cytotoxic C cell will come on to attack, will come to attack to destroy this cell. The T memory cell is actually laying in circulation waiting to be activated, and once it becomes activated, it will divide so that it can then go on to activate B cells and mount an immune response. And regulatory T cells are meant to prevent an immune response from going unchecked. This is preventing from an overly stimulation of T cells so that there is not an autoimmune process going on. So from this, I want you to take away a couple of things. One, immunity can be innate or it could be adaptive. In the adaptive, we're creating specific immune responses to attack specific pathogens. The fact that we have specific immune responses to a specific pathogen doesn't mean that we have a response to all of the different pathogens. We have to learn them first. We have to learn what they look like. How do we learn what they look like? Through lymphocytes. So we have three main classes. So the B cell, again, is the one that creates those antibodies after they've divided into plasma cells. T cells, there are multiple types. T helper cells, cytotoxic, T memory, and T regulatory cells. Make sure you know the function of each one of them. Remember that T helper cells are the ones that go on to activate B cells for the production of antibodies. Before they do that, they need to be presented with an antigen. And that antigen is presented by some of these cells that are present within those mouth tissues. They are the first line of defense that are encountering some of those pathogens, and once they learn what they look like, they go on to show it to the helper T cell so that they can then go on to activate a plasma cell. Cytotoxic T cells are actually probing your own tissues looking for this MHC1 receptor. And if they see abnormalities within the antigen in this MHC1 receptor, it will assume the cell has either a virus or it has cancer, and it will go on to destroy it. T memory cells are circulating within your body, ready to mount an immune response if activated, and they could become activated either through antigen presentation, the pathogen itself, and T-regulated cells are also in circulation, and they are there when there is an immune response because they don't want that immune response to go unchecked. Lastly, we have NK cells. So NK cells are cells that are in circulation, and they are checking for a lack of MHC1. So the example that I'm giving here is we're gonna go over a cell. We have some tissues right here, and they all have receptors, MHC1 receptors. Remember that these MHC1 receptors are a status card of healthiness, of how healthy are you. So they show what's going on inside of that cell. This receptor is MHC1. This is all the receptors are MHC1. And these receptors, when they are sick, they will look different. When the cell inside is sick, either be with cancer, a virus, there is something ongoing on with the cell, the status will change and it will change. And when the cytotoxic T cell, we're going to put in here a cytotoxic T cell, or a CD8, that is another name. Or we're going to put in here CD8, this is CD4. CD8 will check this, and then it will attack the cell so that it can destroy it. But sometimes the virus or the virus that is inside will become really smart, and it will decide that if the way it is going to be destroyed is by the production of an unhealthy card or an unhealthy ID, then it will stop producing that MHC1 receptor, so that there is no way of the CD8 cells or cytotoxic T cells to know that they are ill. That is, we have NK cells. And NK cells, if they see there is something, if they see that there is a low population of MHC1 receptors, then it will go on to attack it because it knows there is something wrong. There are multiple ways in which we can enhance some of these immunological responses, and that is through interference as well as molecules that communicate the cells to one another. This is a very simplistic view of looking at that immune response. However, these are some of the biggest players into this process. Next question is, blank cells are CD4+. They bind to MH blank on blank. Their function is to, here we're talking about the anatomical name or the name related to helper T cells. We're going to go ahead and write it out. We have different T cells. We have T helper or CD4 cells, which are very important because they go on to stimulate B cells for antibody production. So we're going to T helper cells are CD4, and that is because they have a CD4 receptor in the outside of them. That is what is CD4. Okay, T helper cells. Now, these T helper cells, remember that they are stimulated, or they are presented antigens through antigen presenting cells. That is a little bit different. Antigen presenting cells, whichever one of the four types, will show a receptor through an MHC2 receptor. And it will go on to present that receptor that is here to that CD4 cell. So CD4 is just the name for a helper T cell. And these CD4 cells are activated by when they bind to MHC2. So this MHC2 receptor right here. Remember that the MHC2 receptor is within antigen presenting cells that are going to activate helper T cells. MHC1, it is on your own tissues, and that is a card or an ID to show the status of healthiness of that cell, or what is happening inside of that cell. Okay, so they bind to MHC2 on the outer portion. Their function is to stimulate B cells. Actually, let's go ahead and rephrase that. So this goes right here. The function is to activate T and B cells. So they activate themselves because they want to start division, right? And this is on antigen presenting cells, APCs, whichever one of these four is. Blank cells are CD8, that period. They bind to MHC blank on blank. Their function is to, so here we are talking about cytotoxic T cells. Again, we have different lymphocytes. We have T cells, or T-dependent cells, cells that are born in the bone marrow and then go into the thymus to get trained. And there, about 98% of them get destroyed, and those 2% are in circulation. Those T cells, there are multiple types. We have T helper, or CD4. We have T cytotoxic, and that is CD8, cytotoxic. I'll think that is the more dangerous is the higher number. That is a good way to remember. We have T regulatory, which means that it helps regulate that immune response, and we have T memory. We talked about T helper cells as a form in which they are activated through antigen presenting cells, showing an MHC1, MHC2 receptors. Antigen presenting cells use MHC2 receptors to the CD4 cells, and the cytotoxic T cells, CD8, are probing for MHC1. All right, so we're gonna put in here cytotoxic T cells are CD8. They bind to MHC1 on regular tissues, on self tissues. Their function is to destroy infected cells. So again, cells display MHC1 proteins on their surface. When the MHC is normal, there is no response. If that healthy card is showing that the cell doesn't have any viruses, or there is no cancer within, then there is no response. But when the antigen is abnormal, either there is a virus inside of that cell or there is a cancer, that type of card will change. Remember that we have a cell here and we have our MHC1, and our MHC1 will change. Its ID will look different if there is a virus in here. There is a virus. When the cytotoxic T cell comes in, it will be stimulated and then will cause the attack of this cell. Cytotoxic T cells, once activated, they cause the apoptosis of that cell. All right, and they cause the proliferation of T cells to that specific antigen. In summary, cytotoxic T cells are CD8. They attack foreign cells or cells infected by viruses or cancer as well. Okay, let's go over this process one more time. We have a cytotoxic T cell and a helper T cell. The cytotoxic T cell is probing MHC1 receptors or checking the MHC1 receptors in self tissues. In this case, this type of cell that it found is infected with some type of antigen. So that antigen that is being shown right here is activated. Now it's activating this cytotoxic T cell, causing a response to lead to apoptosis of this cell. Remember that the receptor that is being used to recognize this antigen is MHC1. So CD8 cells are probing the receptors of MHC1 on your regular cells. On the other hand, we have helper T cells or CD4. CD4 cells are helper T cells, and these helper T cells are waiting to stimulate an immune response. And they do this with the help of antigen presenting cells. We have antigen presenting cells that have in their outer membrane an MHC2 receptor, and they activate this helper T cell by showing what the bacteria looks like. You see this triangle right here? It is what this triangle is right here. He broke it down and then he's presenting it to the T cell, to the helper T cell, so that then it goes on to activate a B cell, so that then the B cell divides into a plasma cell, and then it creates antibodies that are targeting that triangular portion that it was shown into. Let's go over this process one more time. We have different type of cells. We have antigen presenting cells, and these are cells within lymphoid tissues, and such as mouth tissues. We have B cells. We have B cells. We have macrophages. We have Langerhans cells, and we have dendritic cells. So these cells, once they encounter a antigen, all right, they will use in their outer membrane or their MHC2 receptor, they will use that to show what the pathogen looks like. Macrophages will do that by engulfing the pathogen. B cells will do that by carrying memory from what that pathogen looks like. B cells that are activated go on to present to also T cells. So once a B cell has been activated, it can do multiple things, such as divide to become a plasma cell, and or going on to activate other T cells. But nonetheless, it will use that MHC2 receptor to cause the stimulation of those other cells. This one's the same. Now, once we have that, then we have a series of T cells. We have T cells. We have CD4 and we have CD8. The CD4 molecule, the CD4 cells are going to be activated through these receptors. And once they become activated, they will go on to other B cells, so that those B cells can then divide. And once they divide, we're going to have a portion that is going to become a plasma cells, and a minority that is going to become memory B cells. And these plasma cells will go on to produce antibodies. And these antibodies, once they are in circulation, that is going to take a while to mount that immunity, But once they're in circulation, the next time this pathogen comes around, when the pathogen is flowing around, this antibody will bind onto the surface of it. The activation of this antibody will cause changes that will then lead onto the activation of the complement system. The complement system will become activated. So we will have C3 molecules. Remember that we have C3, which is a protein that is created by the liver, and it is free in circulation. Now, once it comes into contact with this antibody, it will then become activated, and when it becomes activated, it breaks into two, C3A and C3B. Remember that C3A is for inflammation. It's going to go on to stimulate mast cells and basophils, amongst others. But once you stimulate mast cell and basophils, you are increasing the release of histamine and heparin to increase that immune response. You are now wanting to recruit immune cells to this area. And the C3b portion of that complement protein is going to bind to this. Right? And it's gonna bind. And it's gonna opsonicize this molecule. When you opsonicize this pathogen, then it is a lot easier for the macrophage to come and engulf this and digest it. Alright? What this complex could also do, other than opsonization, it could then go on to form a larger membrane attack complex. So it will bind other membrane complex, and this membrane attack complex will then create a hole within this that will lead to the release of all of the elements and all of the organelles and electrolytes within that pathogen, so that it will burst and it will cause cytolysis. So this complement that is now activated by the antibody could destroy this pathogen in multiple ways, either by cytolysis, creating a hole in that, opsonization, where we are now putting a lot of C3b molecules and the macrophage can engulf it. We can also activate inflammation, which leads to more immune cells to the response. And lastly, there is something that is called immune clearance. So that is that once you have all these antibodies, they will attach to red blood cells, and the red blood cells bring these complexes of pathogens and antibodies and complement to the liver of the spleen. And because there is a lot of macrophages there, the macrophages will then take all of these and destroy this area from the red blood cell that they were attached to. We'll continue to discuss this a little bit further in the future, but just know that once the complement system is activated, we have multiple ways to destroy this pathogen. So we have the process of Planck describes how B cells activate helper T cells, and helper T cells then activate B cells. This is something that we call co-stimulation. So within co-stimulation, we have antigen presenting cells presenting to T cells, so that T cells can recruit other B cells so that we can mount an immune response. Let's summarize. So we have antigen presenting cells, and we have our 4 different types. We have B cells, we have macrophages, dendritic cells, and Langerhans cells. In this case, we're going to explore the B cell route. So once B cells are in circulation or in the germinal centers of your lymphoid tissues, we can see that once exposed to an antigen, we're going to expose a pathogen. This pathogen will be engulfed, or the pathogen will have an antigen, and this B cell will engulf this specific type of antigen. Once it engulfs it, it will break it down and then put it into different pieces, and it will process it and show it into its outer receptor. And we're going to put it here in purple. Now it's going to show it in this MHC2 receptor. So the MHC2 receptor is then going to activate T cells. So this helper T cell, or the CD4, is going to be activated by this MHC2 receptor with the antigen that this B cell had engulfed. Now the CD4 activated T cell, once activated, is going to activate another B cell. And once it activates this B cell, then the B cell will start, we'll put it here, activated, will divide into multiple B cells. We're going to put here B, 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 B. One of them is going to become a memory B cell, and these other will go on to become plasma cells. And these plasma cells are the ones that are going to go on to produce antibodies in circulation that will target this specific pathogen. So these antibodies that will be in circulation next time will bind and it will fixate to this pathogen. Which T cell inhibits the immune response? So we have different types of T cells. Remember the function of each one of them. We have T helper or CD4. We have T cytotoxic cells, which are also CD8. We have T regulatory and T memory. Now, what are these T regulatory or suppressor cells? They limit the immune response. If you were to produce a lot of antibodies without check for a pathogen, you may cause mutations and you may end up developing antibodies against your own tissues. So you want regulatory T cells to downregulate this response to limit the immune response so that we can prevent autoimmune diseases. Which T cell remains to give immunity upon secondary exposure? So as we mentioned, we can have memory cells once the cells are activated. So we have lymphocytes, and we're going to focus mostly on T cells and B cells. So once T cells become activated by antigen presenting cells, so we're going to put in here activated, they go on to stimulate other cells, but they will divide first. And then out of those divided cells, a great portion of them will go on to their task, but some of them will go on to become memory cells that will remember that immune response so that when they become activated, they will work quicker. The same goes for B cells. Once they become activated, they will start to divide, and some of them will become memory cells, memory B cells, and a great portion of them will go on to become plasma cells to create antibodies. But the circulating memory B cells and T cells will stay in your body for a long time, and this is what is going to give you long term in the long run, because when this memory B cell in the future becomes stimulated, it will be a lot easier than to retrain your immune system all over again. So these memory T cells in this case are going to give you immunity towards a substance or a specific pathogen. Antibody functions. Block pathogenic region of a pathogen antigen. Blank. Bind to antigen, complement proteins to antibodies, enhance phagocytosis or cytolysis. Next, antibodies bind to multiple antigen molecules, producing a complement that limits the spread of infection. Remember how we talked about some of the functions from the complement system? So here when we block the pathogenic region of a pathogen, we are inactivating it or we are neutralizing. So when that antibody goes on to that a pathogen antigen, we're neutralizing if we're blocking it. If we're now binding the antigen and complement proteins are binding to that antigen, were causing cytolysis. So this will be through complement fixation. Okay, and we'll discuss each one of them one by one. Fixation. Antibodies bind to multiple antigen molecules, producing a clumping that limits the spread of infection, and that is agglutination. All right, so let's look at the first one. So if we have a pathogen, which is a recurrent offender, is been on your body before, you have already antibodies against it. So when it is in circulation, there will be antibodies that will be sticking to this portion. So by doing so, these receptors won't be able to work in any other part of your body. The pathogenic sections of this antibody will allow it to communicate with other cells. But if we prevent it from communicating with other cells, we are neutralizing this agent. Next, if we do a complement fixation, once the antibody binds, there are going to be changes to that antibody, and complement proteins such as C3, which is free flowing on circulation, is going to become activated. And once it becomes activated, we're going to go into C3A and C3B. C3A is going to activate inflammation by activating basophils and mast cells. And when we activate basophils and mast cells, we're increasing histamine and heparin for the recruitment of immune cells, and we're now causing inflammation. All right. Now C3b is a different ball game. Within C3b, we're going to go ahead and then stick onto this portion right here. And when we do that, we're making it easier for macrophages to engulf it. So a fellow macrophage can then eat this guy up a lot easier. So complement fixation. One here that we're missing here is that once we have a complement fixation, we could create a membrane attack complex to cause cytolysis. All right. Oh no, actually it's right here. Phagocytosis or cytolysis. Now last we have antibody agglutination. So within this, we don't have to have those complement proteins to activate complement system. We could very likely just have antibodies clumping onto each other and clumping onto other types of pathogens. So when you are clumping them all, sorry, let me just erase all of these real quickly. So when you are clumping them all, they become less effective. They cannot migrate. They will have to stay there. So we have a cell here, a cell here, a cell here, and we have different receptors. We have now antigens, we have antibodies that will bind them together. And they will agglutinate them, creating this huge clump of bacteria. And then they won't be able to migrate onto other tissues. Know what B cell and T cell activation occurs in the nodes and the spleen. The spleen checks for pathogens in the blank. The nodes check for pathogens in the blank. So the spleen is checking for pathogens in blood, and the nodes are checking, lymph nodes are checking for pathogens in the lymph. Remember that we have sinusoid capillaries within the spleen, allowing red blood cells to be probed by macrophages. Macrophages can check the red blood cell status and take away any of the possible bacteria that may be fixed to the outer membrane of that red blood cell, or actually engulf red blood cells that may be ready for destruction. But overall, we have macrophages within sinusoid capillaries within that spleen that it is being, we're checking for pathogens. And we have lymph nodes within the lymphatic system that it is rich on B cells, T cells, NK cells, and we're probing it for pathogens. Next, HIV leads to a destruction of blank cells. This impairs the immune system. AIDS occurs when the CD4 count is blank. And next, patients with AIDS require or AIDS will eventually die because of blank infections or blank. So for this portion, this is talking about the disruption of the entire immune system through the destruction of CD4 cells. Remember that CD4 cells are activating B cells. They also activate macrophages, and they also activate T cytotoxic cells. So helper T cells or CD4 cells play a huge role in coordinating that immune response. So if you don't have helper T cells, it will be very hard for your body to create antibodies against a specific pathogen or the virus. We'll have an increase in opportunistic infections because macrophages won't be able to destroy those pathogens because they won't be activated. Macrophages are activated by CD4 T cells. Cytotoxic T cells are also enhanced by the activation of T cells. So if we do not have CD4 T cells, cytotoxic T cells will be downregulated. They don't work as well. So we have an overall attenuated or decreased immune response the less and less there is. And that is why AIDS is so problematic. AIDS occurs when the CD4 count is less than 200 cells. Um, when AIDS happens, now we have opportunistic infections that will take over. So infections that can thrive on a low immunity system. Your body has a nutrient-rich environment, so the pathogens will thrive in this section. Now, if there is a poor immune system, there will also be a decrease in surveillance for cancer. So there is also a risk for a cancer, mostly Kaposi sarcoma. Now, some of the medications that are used in HIV are aimed at attacking how the virus is spread, such as replication of the body, such as replication of that virus. Now, last, blank is an autoimmune disease in which the immune system attacks healthy self cells. It often produces a butterfly rash on the face and joint pain. Here we're talking about lupus. So lupus is a chronic widespread autoimmune disease in which we're creating antibodies against healthy tissue. These antibody antigen complexes accumulate and lead to widespread inflammation. When there is widespread inflammation, then we're destroying a lot of healthy tissues. Remember that we're activating neutrophils so that they can release chemicals that can then damage your unconnected tissues. Some of the key signs or bell ring signs are butterfly rash in the face, pain, organ failure. Lupus is not contagious. It is sometimes genetic or associated to specific traits, such as being a woman or Epstein-Barr virus. There is no cure for this. Some of the treatments related to lupus or autoimmune diseases are medications to attenuate your immune response. So if we attenuate your immune response or lower your immune response, then lupus activation or that autoimmune process will be less pathogenic, less problematic. All right, this brings us to the end of our review. If you have any questions, please email me.